So we have done one exercise with TensorFlow that to find which activation function is better, right? So what will we do is we'll do almost similar stuff with your this guy Keras now. Okay, so that we get to understand how to start because key writing Keras code is pretty simple, straightforward. Just few foundational things are there. I'll just rather than writing a very low level code with TensorFlow, I'll write it one with Keras so that we get a complete picture what is happening. Okay. Yeah. So here. Finding the right activation function. Okay, so here also we'll try to compare between right. Again, I'm using this analysis. So let's see what is happening. So using scikit-learn, you are calling this function train and test, plotting the graph. Okay. Now we have these few important things in Keras. Keras.model sequential. So this is something using which we will be creating models. Okay. And sequential means one after connected to one after another sequential graph. Then you have Keras.layers dense. This is what tells you how connected this layering of network is. Okay, dense means fully connected.
So the dense will give about
each node is connected to all the nodes before it and
input and output.
Right. Dense is the way of connection. Sequence is pattern of connection. Pattern means you have one layer. I mean, you have how many layers you have. Okay, what is the relationship between the layers? Those things are sequential. Okay, the dense means each node unit is connected to how many all the units before it and all the units after it. Then you have two categorical. This is used to convert categorical data to integer data to categorical data, and so on. Okay, and a lot of other utilities are there. Then you have Keras callback. Okay, callback for a string callback function. Then you have this is a seed so that it generates same data every time. Okay, and Keras dataset import amnesty so that we have amnesty to work around with.
We don't do dummies here.
Dummies,
we don't convert categorical to dummies.
We'll do, but this is amnesty data.
But usually does it?
Usually we'll do.
Because we have seen the other day you were doing fit underscore transform, which converts the categorical to numerical.
So whenever you have categorical,
so rather can I convert it into dummies and do that?
Dummies, the way that we did it using label encoder. Yeah, you can do that. If you have categorical data and if you think the data is within, the category is within 5, 10, 15, 20, okay, the label encoder works there.
Okay.
If it is much more than, if it is text and all that, then you have to resort to other mechanisms, like your TF-ID vectorizer and all.
Right.
Keras is not installed. Okay. Let's do some data set.
So Keras, can you want to call this is called Keras or that's not okay?
Module Keras.
I think Keras is built along with the TensorFlow. Yesterday I tried in the Google Cloud. TF.Keras, it is working.
TF.Keras. I was trying to use independent Keras. Wait, I think the installation, the other version had it here. Yeah. This is the old way that you see now.
Here we do pip install Keras.
Hmm.
So you should be connected to the network to so it will directly
Download the Keras and install it here directly.
So how it knows the path from where to download
That is there. That will be there in the package manager actually.
in the pip actually.
Pip actually uses PyPy, APIs.
Oh, okay. So
It directly just checks there if there is something like Keras, download it from there. Okay.
But in the linear regression code you have shared with us, we didn't split the data into test and train.
Yeah, maybe for simplicity. I think.
But here you wanted us to split.
So that we can get that. I mean, linear regression, we are more focused on understanding linear regression. But this is about actual process, right?
If I don't want to split data into batches, if I don't want to split data into batches, I don't need to have this randex and random. So directly I can pass data here.
Yeah. So just that every time when you're training the model, you need some piece of not the entire data, some piece of data with you, so that you train it, get some cost, then train it, get some cost. To repeat this process.
But that's a better way of doing, but still I can do it this
in
way.
one shot.
One shot.
Without for loop.
I'll take for loop, but I'll not take this random index. Random
Then
index is splitting into batches again.
No, random index is choosing random data, how many times you are mentioning over there, right? Okay, so if you're doing so,
then for loop is also
yeah.
not needed. Yeah. So this is the best way of doing it.
Yeah, this is best.
Or if I don't need batch size, I don't need for loop as well, right?
Batch size so that every time you are actually
random.
I believe this is installed in the right place. Let's check because there is.
Install.
Yeah, so I just want to see if where it is installed. Installed this series Keras Aconda version users app data, m data. Installing in app data only. Let's see now. It's on.
Under scripts, it's not the Keras was not there. Under Keras.
So actually, on doing the tip direct installation, okay, it was actually yeah, it's fine. It's added now. It's fine. Okay, now it is fine. Successfully installed. So requirement already satisfied. It says it is installing in the same directory. Site packages. Okay. So
I think all the packages are in the same.
yeah, so I before running, I just wanted to confirm this. So I think it is lib.
Site packages. Anaconda 2 you actually.
Oh yeah. No, I had both different versions. Yeah.
Site packages.
See, Keras of the directory. So I do this check before, and if everything is all right.
So Jupyter itself is an exe.
It is an exe actually.
That makes sense.
Everything is little different. I mean, it goes to site 8888, right? Okay. So you can see here now Keras is using TensorFlow as a backend by default, right? So I'll load a bit. I think it is finally loading this in list. Yeah. So this is using Keras as a backend. Okay. After this is done, I'll execute this line, which will be like whatever MNIST data we have, right? It will be loading an X train and Y train. Okay, so you can see here X train, Y train, X val, Y val. It is loading this data. So we'll see what is content, what it contains.
So it automatically splits the data, is it?
Yeah.
Which percentage?
I think here equipment.
That's a default behavior.
Default. Which one? Yeah. Not default behavior. This data set it has
the columns.
Right. You'll see here it is downloading.
You can print it out.
Yeah, you can print the data also. So first it is downloading this entire information. Extreme dot. Right, so we can see 60,000. Okay, then xval 10,000. Fine, right? This is a train data test.
Is the dimension
28 is the dimension.
So we have 60,000 images with 28 dimension.
Totally 70,000.
Right.
And
10,
20 maybe.
Yeah, 70,000.
Does MNIST have such columns or?
Huh?
Does MNIST dataset have a column?
No. It has actually here we are loading from Keras datasets MNIST. Okay. So they have when you load data, they actually in Keras it is dividing the data into two parts. Okay. Inbuilt to Keras. You don't have to do that.
Oh, that's what I'm wondering. There are no keywords you have used. How it does.
Right. That's not.
Because then you are importing.
It's a standard data set, but if you want to use our own data set, then probably that you will just.
Okay. So now what we want to do is we want to plot all the numbers now. Okay. I mean, not all the numbers, unique numbers now. Okay. So I have a matplotlib code if you want to refer it as. Okay. Using this, right? Okay, so what it is doing, unique label from Y train, it is finding the unique label, first time 0, first time 1 using set, right? And it is creating a plot of size 12 cross 12. Each is 12 cross 12. But for each unique label, what it did is from unique label, Y train to list index and label information it is getting. Right? From unique label, it is getting index number of each label. You can say 0, this 5293 is index number, 679 is index number. This is getting the index number here. And you are getting the image. You're plotting that image excess of this. So there is no excess information. Title 0, 1, depending what it is. Okay. Sorry, 0 is the first argument. That is where this data is coming, label information, actual label. And index number is coming from here, and you're showing a gray image. So this is like just showing the entire contents of data in simple lines, pretty much matplotlib code, right?
So here it's 12 cross 12 is the
size of each. Okay.
And what is this 10, 10? That subplot where we are doing. There's a plot dot subplot 10, 10.
Sorry. 10, 12 is 10, right? Figure size as a mode 2 can come. Okay, so 12 cross 12 means it can be possible 12 subplots. Figure size, each size of the figure, right? And subplot 10 cross 10 is the size of this actually. I mean, how accessing this 10, 10, 1. Like first time it will be 1, right? Next time it will be 2. Next time it will be 3. So 10, 10, 1 is this guy, 10, 10, 2 is this guy, 10, 10, 3 is this guy, 10, 10, 4 is this guy.
So that I got. So 12 cross 12 is the total. So it can have the figures of
12 cross 12. Yeah, I mean you can have a lot of images here actually.
Okay.
I mean pretty much controlling what this matplotlib is doing actually.
Okay. So here is 0 colon the index. So this image 0 is in the 5923 row. So it's pretty 59236742, right? All the 0 colon 5923 means
0 is at 5923 index.
0 is at 5923
index. First one of the zeros. There is
yeah, it can be. Yeah.
Right. One of the zeros is here. Just plotting this information. If you have any doubt, let me know. Just plotting this information. Okay. Now, what is the thing that you want to do? You want to normalize the data. Remember, when it we diminished, we normalized it, right? Min, max, all those categories. I'll just copy paste the same photo value. Min, max, and all that. So what we are doing here, we are normalizing the data. What I'm more interested doing here is that Keras part. Okay. Okay. So here you can see you are dividing the data by 255. Understood, right? As type, first it converted xtrain into float, right? Then you divided it by 255. Fine. So that your pixel value comes between 0 and 1.
0 and 1.
Fine, right? Okay. Then understood, right? This is you're changing all the feature data into this. All the feature data is now changing to this.
So that pixel data you are converting it into float and then you are dividing by 2.
Yeah.
Will there be any loss of pixels?
No, nothing. No, float is just adding. You can. Earlier I think we multiplied it by 0.0. Sorry, 1.0. Same thing. Just that you're first converting the type.
Image you can convert to a number and you can divide.
Remember, each of the values is between 0 to 255. Each pixel value is between 0 to 255, right? In MNIST data, and we are just converting here. Then we had a lot of. If you see the data, Y train. You can see here, this is this, right? 50. This is the class number. Fine, right? This is the class number. How many possible classes are there? 10. Okay, so what we have to do now? We have to do now the mapping of numerical data to categorical data like this. To categorical using Keras. If you now do Y train, it converts that into vector. Understood, right? Earlier case, when you're pulling the data, that itself we did enable this one hot is equal to true.
True. Yes.
Right? Now here we are converting this numerical data into categorical data like this. What is the shape of this? Y train I printed, right? 60,000 comma 60,000 comma each vector of 10.10. Right? Yes. Understood, right? So each vector here, the series data. This is a 10 null. So if the second data means 0, second data is 0. That is why first element is 1. Fine, right? So this is our output. If we compare it with our here, see how we pull the data. Here we we didn't do it. Maybe some other some cases we did it. But here what I'm trying to say, you remember in classification in neural deep neural network, we need output to be in the vector format, right? That is why we are calling this guy to one hot vector labels.
Okay, output is in vector.
Yeah, one hot vector labels. Okay, so now the next point. Okay, we have to flatten the data, right? So what are you doing? You're flattening the 229, 28 cross 28, we are flat, reshaping it to 784. 28, 28 was one matrix, right? We converted to one row. Each row is of 784 data as a input feature. Output is 10 vector.
0 to
99, 10 vector. That's what we're doing it here.
So here we are hard coding the shape. We can give it as bracket like how we do it in other placeholders and try to. So 60,000, since we know that data we are doing. So if you don't know the what is the
no, I haven't yet created a placeholder and all that here. I'm just this is the simple numpy here, right? Okay, so we are. See, you might have seen I'm not. I haven't imported a lot of TensorFlow stuff.
I see. Yeah.
I haven't imported any TensorFlow. So all this will happen in the backend. Okay, now we want to create the model. Right. First, we want to see with sigmoid.
Activation function.
Yeah. Model. Sigmoid is equal to sequential. Okay, so what we want to do, we want to try with many layers now. Model sigmoid dot add.
Where we are giving how many layers?
Exactly dense. Okay, so how many layers? First layer was 700, right? 700 input. First layer, I mean, our first hidden layer. Okay, and input to this is input dimension is equal to 784. Activation. That's it.
So then 700 means 700 nodes in the hidden layer.
Yeah.
One hidden layer.
First hidden layer.
First hidden layer.
Right. Okay, just keep adding to this.
So if we given another one statement, then another hidden layer will get created.
That's what we'll do now actually. So this is the first layer. If I want to add or more hidden layers, this is all you have to do. 700, 350. Okay.
Oh, no need to mention the dimension.
Okay, so yeah. So from you're reducing the number of layers, right? Seven 784 neurons in the first 784 neurons in the first neural layer. This is the first hidden layer, the second hidden layer, third hidden layer, fourth hidden layer. Okay, and at the end, yeah, we'll have
future layer also.
Future's
first layer.
First layer, yeah. And this is your final layer. Yeah, softmax you're applying here because it is classification output, and after that, okay, you want to apply statistic gradient descent, right? SGD. SGD is for okay. So you do this model sigmoid compile categorical cross entropy. This is the mechanism that you are using in finding this is the optimizer. It is a matrices.
Okay. So we do the GD, the gradient descent you are doing, right? So what is the
same thing. So here you don't have to call the run and all that. This is done.
Yeah. So that so what is the difference between SGD and the GD? So gradient descent is stochastic gradient descent.
Right.
So both are same.
A statistic gradient descent is the one that is majorly used. Statistic gradient descent uses the concept of batches. Okay, every time you will be passing some data, training the model, using the output to do another. So batched way of doing it, right? That is your statistic gradient. Gradient descent is a general concept. Okay, statistic gradient descent is a mechanism by which you will be implementing, and there is some differences here. That you will be doing the training with this much amount of data. Whatever loss is coming, you will be I mean, this process of batched processing is known as stochastic gradient descent.
Okay, so there are gradient descent. There are many types.
Many types. I will see that actually. Okay, Adam gradient descent. I mean, Adam optimizer. Many more. Let's see 7 types of optimizers. See. So this is what is creating your first model, right? Model creation. Then of course, I mean, you want to create a model for ReLU also.
So you show this accuracy, everything it will just
all in one shot. You choose. I mean, these are very highly configurable parameters. You can try with all of them what you want. Okay, you just have to mention the ReLU thing here. Yeah. So now we want to compile this model with SGD.
So here we use categorical cross entropies because the values are in categorical nature.
Yes. Okay, then
you need to train the model using sigma separately enabled.
okay. So now you can see what I'm doing here is very useful. So we are creating a class history loss and we are implementing this callback function. Okay, so how it happens here is on train begin. So this function, this will be callback class. That means every time the training ends, this function will be called back, and whatever we are doing here, it will be doing the needful. Okay, just let me show how it is getting used. See, this is a callback class. It is extending the callback class in Python. This is how your inheritance works. This is extending this callback class. This is on train begin. You're overriding this function on train begin. On train begin, you are creating this placeholder here. I mean, creating a variable here which will hold the data. Self.losses. Okay. Then logs. So here you are getting anyway the data, and here batch loss you are getting it. Batch loss, logs get loss. Okay, and you are appending to the losses list. Fine, right? Okay, see, I mean, let me show how it is getting used. When you call this function logs, what will it get and all? Okay, just see this placeholder. Just keep. Okay, these are your various epochs, batch size, validation split. Fine, right? Epochs, batch size, validation split. Okay, then what we intend to do is say this. Now epochs means number of times you will repeat this entire stuff. Batch size is at every epoch what is the batch size of the data. Then validation split means when you're training at every epoch, okay, you have some training data with you. Is that data also it will find accuracy. So it will divide the data into 80-20 and it will find the accuracy after every epoch using 20% of the data. Understood, right? So you see here, let's see this, it will be out clear. So history loss is that class. So what you're doing, history sigmoid is the object is getting created here. Fine, right? Okay, an object is getting created here. Then you have fit function x train, y train that is expected. Epoch is equal to number of epochs, batch size is the number of batches. Callback is history sigmoid. That means this is the function which will be called back and the rest of the stuff will happen. Logs get lost. So using this data, it will get the lost, stored it here. validation split. The validation split is here, 0.02, verbose is 2. So if I run this, see, train it 48 is 80% of training data. 60,000, 80% is 48. Okay. So the number of epochs, 1 of 10 it is running. And it will give you accuracy also.
How do we use that history? We already have the structure, the last function called the sigmoid function. So we are again creating the history dot last, right, where we use the callback. So what is the difference between this class and that? If we can print that class or that also, we give the last only, right?
Wait. So we don't have direct. It's a very encaps.
Here we have the last already categorical.
Yeah, we are no. Here we are not. Here we are telling it use this loss mechanism to calculate its own. See, in this case, we are compiling the entire model and creating the connection, the core, the low-level code for it. Okay. Here you are passing this class so that it uses. I mean, basically, what happens when you do here? What happens when you do here? This is the only place. I mean, see, you are not calling any run session. All those things you are not calling. Okay, but you need a mechanism. You need a way to internally go calculate loss and few other things, right? For that, you have this callback function. Okay, in this callback function, you have. I mean, we'll see that as we, that this callback function will have many implementation. Itself is taking a lot of time. Just one. See, because of the number of layer getting increased, it's taking
700 all the. So one batch of iteration.
See, because of that, see, you gave loss function in it, right? Because based on your loss function, it is calculating accuracy to be some at least at this point of time 0.1, 0.10, 0.11. Let's see how it proceeds. Right, this is how it will show you. Okay, this is validation accuracy. This is the training accuracy, and this is the time each. So you can see here, right, much more clear level of information. And it is sigmoid, so it will converge very slowly. That is why should I?
Yeah, so sigmoid will take time.
Take time, yeah. Whereas in case of ReLU, it would have converged so far.
So the layers are more, right?
Yeah. But you can see here, right? Code writing just became easier now. You don't have to take care of those, session variables, placeholder. Right? You don't.
There is no placeholder.
There is nothing in that because it's abstracted. It is more of a scikit-learn API, right? More of any machine learning API. I could have executed.
You cannot stop in the middle.
And the entire notebook will stop.
I think it's another fight.
Okay, let me write the other code here. Okay, this is for sigmoid, so you pretty much expect just the callback function is something that is new. Most of the other things is what you are expecting, right? So
now we'll do a prediction.
No, we'll do for ReLU, same thing. Now no changes in the code, isn't it?
Only the instead of the function, we have to call model ReLU.
Right. Okay. And after this, we can plot the graph.
Prediction, yeah.
Yeah, prediction also the model name dot predict.
Oh.
Okay, I'll do this.
Yeah, from two of the will predict it.
Yeah. Okay, so I'll just try to see if I can stop it. Okay.
The path is there.
I've stopped it, I guess.
Yeah, interpreted that.
Hmm. Because of this stopping. See this error. Let's see this kind. Okay, let's see the. It will converge very fast. I mean, I think in fifth or sixth iteration itself, it will be reaching around 90s. See, the accuracy itself is in first iteration itself is around 60% accuracy, right?
Yeah, this point one.
Yeah. Okay. Let's see a couple of more things, then we will.
Validation.
So we have to see both that's accuracy and validation. That's a train accuracy and this is the test accuracy.
Test accuracy, validation accuracy is more.
That is what we have to
Oh yeah,
with the test samples, right?
that is yeah. 84, 88.
So here when you check the accuracy, so when it reaches 99%, even the loss should come to zero or like how is the
I mean, if it is accuracy 100%, loss will be
zero?
zero. Not this is a classic case, right? So not necessarily zero. It will be very low.
It will be very low, yeah.
It is closing towards 90s, right? To wait it to reach or finish, else the model will be. Predict is nothing but model name dot predict. You just have to pass X data here. That's all. Okay. If we let it happen, we'll
You do.
one more thing. No, we cannot do predict here directly without training it. Okay, let it happen. By the time we'll touch upon one more topic. Okay, so you got a hang of how to write Keras code, right? I mean, more or less. Okay, so now okay, so we'll learn one more concept. We'll learn concept of regularization and dropouts. Okay, regularization dropouts. Some little bit concepts over it. We'll do that with some example. Actually, might be hearing about bike data set. Bike data. Let me untar it. Okay. So we have this data. Inside this bike folder, we have day, hour data, right? Okay. Last one, right?
Was 93. Change the data. Notebook. Keras and the bike data.
We have a few concepts we'll touch upon here.
So doing this in the TensorFlow also, like on the like dropout, we can now do it in the Keras.
Yeah, dropout you can do in TensorFlow also in Keras also. Okay. So dropout, maximum. I mean, these all are generalized concepts. Actually, if you want to do dropout, then you have to write those code, low-level code yourself. Okay, you don't have high-level APIs which could help you writing that in TensorFlow. Okay, so this is like you have this like library and like okay. So the first concept is adding dropout to prevent overfitting. Okay, so let me explain what does it mean. I'll use an example to explain this thing. Okay, so this is one of the regularization method. Okay, one of regularization method.
So you're basically dropping out neurons in some of the layers.
Okay, and what does it do? Okay, so this dropout mechanism, right? It forces neural network to learn multiple independent representation. Okay, see, you have edges between two nodes, right? So what happens now? You have once you have learned it, okay, you'll keep on changing it, right? So basically, what happens once you have learned it, right? Once you have finalized it, I mean, after you have finalized the entire model, this is fixed. This value won't be changed, right? So using some dropout technique, what will you do? Even if one time the entire model is frozen, then also you will try to do other ways to find what is the best value of this. If when you give dropout is equal to 0.5, okay, that means first time the you will do the entire model training twice. Okay, so it's like your random forest. What happens in random forest? You have some parameters, right, which you get in first attempt in a tree. Then you get a air parameter in the second attempt of a tree. Okay, then you create a mean out of it. This is what that is actually.
So this is kind of like a tree pruning actually.
Tree? No, not pruning is reducing the size of the tree, right? Not pruning basically. So I'll just paste this line, which clears everything.
Hello.
Okay, when we are using a dropout of 0.5, the network has to see each example twice before the connection is learned.
So it will run the same thing twice.
Twice.
So by doing this, what is the advantage of the?
Advantage is you get a more regularized value. See what happens. What is regularization in networks? You might get very spiky parameters, model parameters, right?
Mhm.
Right, you might get very spiky model parameters. That means I mean, that is certainly leading to a case of overfitting. Right? There might be some
Then,
parameters. Okay, so to handle that, what you do, you need some to regularize. Regularize means reducing the spikiness of the model. I mean, when the model parameter is too high, you know that it is not possible. You want to reduce it. That is regularization. One of the regularization technique is dropout. That if something is spiky, do it one more time. Then
so then it do a normalization.
normalization, right? Does it mean we are dropping out some neurons in the hidden layer? Not yet. Not yet. We are not yet dropping down some hidden. So you are mostly, what does it mean? We are basically recalculating something. That is what it means. Okay. I mean, once you do it, you do it again. The idea is of recalculating that thing.
But we do it only when we expect that there is a spike, right? If there is no,
If the data, see, if the data is simple, then no problem with
no need
that.
of do
Yeah.
regularization.
So let me tell a little bit, about regularization also, since we are discussing this stuff. Okay. So as we know, okay, maybe just a little bit of a regularization. That will actually, if you know that, then another doubts on. Okay, first thing is overfitting is definitely the biggest challenge, right? Okay, most of the techniques to prevent overfitting is placed under regularization. Understood, right? So all these are not regularization techniques. We in scikit-learn also, or any other library, we'll see lasso in regression, like lasso regression. There's nothing but regularization technique. Okay, I mean, in linear regression, if you're trying to regularize, use this, it will regularize the graph, right?
In this case, I think all this, the hard alerts, all this thing can be found out this way. Because I think recently Amazon has suddenly they see when there's a certain volume of 100, suddenly they one day there's a 10,000 somebody buys it. So fraud
Sales prediction,
transactions.
right.
So I think
You can handle that as well, right? Okay, so what is regularization? The objective of regularization is to reduce the test error. See, many times what happens, training errors is less good, but test error is not good. Test training. Okay, so what we have is training error and test error, right? Training error, that means the loss in training. So many cases when overfitting is happening, you'll see, you should always plot a training versus test graph. Training error versus testing error. We'll do that as a this exercise actually. We'll always see that when you're comparing training versus test, training is doing better, test is not doing better. It is like this. Okay, that means overfitting is happening. Okay, then we do the regularization. Got it, right? Okay. Regularization. Reduce. Okay, so First, let's see, without regularization, what has happens in our bike data. It will be clear. Okay, first let's see. Data is equal to pd dot get csv bike our csv. Okay, so we have, let's see the data. Find it. Okay, so you have this yes, season is there. Okay, so these are your some of the data. Okay, now what you want to do, you want to do some feature engineering, convert the data into something that of your interest and all.
Okay. Do the auto input. The data is in
that format, right? So yeah, so we'll do this feature engineering here. Okay, see this, what is happening. Okay, so this is one hot encoder feature, season, weather. See this. Yeah, so you will convert this into one hot vector, all of them. Okay, dummies, right? We are getting pd get dummies. Okay, these are the features that you are getting into. Then what you're doing, you're concatenating data and dummies into XS1.
Only these.
Yeah, among
so
all.
how are you differentiating the season, weather set, and the...
So I'll do data dot. Right, you can see here. See, this is one hot vector it is doing, right? So that means the season is now broken down into many things. Season 1, season 2, this is one. Understood, right? This HR is within 21, 20 hour, yeah, all the hours. Because we think that these are important stuff. That's why you're converting into one hot vector here, rather than level. Yeah, and after this, if you don't think these are important, you're getting rid of that.
All things are dropping it actually.
Can you show me the season column before feature engineering?
Oh.
It's little above.
Right. I overwrote now, so yeah.
Okay.
Yeah, 1, 2, 3, that will be season values.
Oh, 1, 2,
3, 4.
So
but still it is numerical, right?
It is numerical. See, I mean, when you think that, some columns are very important, okay, you would convert them into one hot vector. The reason is, if you keep it in one column, there is only one weightage in that column, isn't it? If you convert this one column into multiple columns, your January can have a different weightage, March can have a different weightage. Understood, right? That is why one hot vector can, if you know that these columns are very important, and your data is that way, so you can make use of it.
So this will convert to how many columns?
Three columns. Session has been converted to 3. 0, 1, and 2.
Right.
Season has been converted to 3, yeah?
Season, see, I mean, we don't, it's depending on how many seasons are there.
So these seasons are the week rate.
Yeah. Okay, convert it into one hot vector.
So these are all things you
remove.
Drop feature really means we remove all that.
All the things that we have mentioned here, we don't think these are important anyway. I mean, it has converted that into this data. Okay, see, PD converter, and you have to remove all the other.
Data dot drop is numpy.
Data dot drop is your pandas.
You're always going to doing it manually, minus.
No. Don't check out little bit of pandas actually. You'll find this data, manipulation very easy with that.
So here we can directly call data dot drop, or no need to call PD dot data because
No, I can directly call this data dot drop. Okay, just have to mention which columns that you're interested in dropping. Okay.
Code is so simple actually.
Okay, then we want to do some normalization. Just quickly, let me at least show the difference. Okay, document it. Okay, this is just normalization of the data, these columns. Okay. Standard deviation, reducing the standard deviation. So if you see data now, okay, you can see here.
It's normalization.
Normalization happening.
Normalization of the
All these columns.
you go before the participant value, then come before you put the data that's
Oh, it's converting comparison to negative.
Yeah, right. Okay, so see, I mean, in here, I'm breaking data into test, train, and split. After this, split, train, test, and okay. So I just does that pattern. When I can check it. So now is the important part that I'm interested in. Now I want to create a neural network with my Keras, right? Okay, don't worry about that part. If you see, I mean, just splitting the data into 3 parts, nothing much. Network architecture. Network RTCDUI. Okay, now that we are done with these 6, okay, so we want to train it basically.
So this is a linear regression.
Yes, linear regression. We want to predict how many, the last column here.
What is the target or value?
Target we broke down here, right? Just distance actually. This bike ride predicting, based on other parameters, what will be the bike ride and all that. The distance here. Y train, cont, CNT. Y train. This is the distance. This is the thing that we want to predict. CNT is the prediction. Okay. Now what we intend to do is we intend to plot it. We intend to run it. Okay. Okay, we need little more iteration so that we can see that this difference 4,000. Okay, we need to see the difference here. Okay, so it will take some time. It will take some time. It will take some time. But we need to plot this. So either I have to leave it here because it will take some time, and we will see this graph like this. Training it, then we'll understand that it needs regularization.
Oh, okay. So
okay.
we are not applied to the regularization.
No. This is we have to see it first.
First.
That it is not working. Then we'll apply regularization. The 2 techniques we learn. One is L2 regularization. One is dropout. Okay, using these 2 techniques, we'll see are we curtailing the regularization or not. Because all of these has finite details. Okay, I'm just trying to touch few of those now. Okay, I mean, if you're creating a model, it's not. I mean, we have worked on simple data sets. Like this is not a real-time data set, right? Then we'll see some, mismatches happening. That graph. After that, we'll try to more fine-tune it. Okay, it will take some time to happen. Understood, right? So far. So understanding. regularization. It will take some time, easily, I think 20-25 minutes it will take. Okay, good. Try those stuffs. Try this without linear regression, the previous problem.
Oh, yeah. That last one.
Right.
What about that one which we ran that our
Let's see that.
Keras.
It reached till 93.
22.
Okay.
95.
Yeah.
93. We can do
So it let's just do this predict. Okay, pass the data here that you are interested in.
pass the model or just the
Data. Extreme.
Zero to 10.
So here you can see here, it is 10 classes, right?
0 to 9.
Yeah. So here you can see this class is around 75%.
So we have to do out of.
So what you can do is you can find a NP max of this guy. Understood, right?
Argmax.
NP argmax, yeah.
Round comma was right.
The argmax. What happened? Sorry. For each element you have to call argmax, not the entire. Will this help? No. But yeah, for each element you have to do it.
So again for loop.
Yeah, for loop or just do that. Okay, for each. Like for example, okay. You want to know what this is? This is 5. First data was 5 anyway, right? Fine, right? This is the prediction. Got it, right? Try it. Let it happen. Let's catch up tomorrow. Okay, guys. Let's catch up tomorrow for this. Rest of the stuff. Thanks.
Can you upload the video? Hello.